All right, so the purpose of this video is to demonstrate how to use the t-table. So we've been using the z-table for some time now. And of course, you can use your graphing calculator if you have your graphing calculator to reach the same conclusion. But most of you guys are using a z-table, and we're familiar with that. But now, when we have moved to chapters 8 and 9, we have a t-table. Now, the t-table is a little bit different. It's the student's t-distribution. We've been working with the standard normal, what we usually call the z-distribution, the z-table, that kind of thing. But we now have what's called the t-distribution. Now, basically, you just need to understand that a t-distribution, well, first of all, I shouldn't say distribution. I mean, everybody does. But what we should say, though, it is a family of distributions. So, in reality, these are going to be terrible drawings, but essentially there's a different t-distribution for every different sample size. So if you have a sample size of whatever, and then another sample size, what happens is that the distribution gets taller as the sample size increases. And then this is actually a terrible drawing here, because what should happen is, I should be careful here, and basically it gets taller, but remember the area under the curve has to be 1. So as it gets taller, what happens is there's more area concentrated here in the middle and less area in the tails. So for small sample sizes, turns out the t-distribution has thicker tails. That is, there's more area, which represents greater variability away from the mean, but as the sample size increases, as we know, there becomes less variability in the sampling distribution, and so you have less area in the tails and more area towards the center of the distribution. But just for the sake of argument, we're typically going to draw a t-distribution just like we would draw a z-distribution. Again, that's a terrible drawing by me, but you get the idea. In general, the t-distribution, just like the z-distribution had a z value of 0 in the middle, t equals 0 is going to be right in the middle. The t-distribution is symmetric. That's the same thing, same as the standard normal z-distribution. And the tails extend indefinitely forever, just like with the standard normal distribution. So there's some similarities here, mainly the symmetry, and the tails extend forever, and it's still a bell-shaped curve. Now, the difference, the main difference is going to be is that for small sample sizes, the t-values are going to be very much different, because again, a t-distribution has a different is a family of distributions, has a different value for every sample size. Now, how do you use this chart? Okay, well, there's the z-chart. So we want to be able to find probabilities and find these things called critical values, or just in general t-values, in a similar way to how we found z-values and probabilities using the z-chart. But there are a few key differences. First of all, notice that there is this column over here labeled degrees of freedom. Well, it's labeled DF. DF stands for degrees of freedom. Basically, degrees of freedom is calculated for us in this class as sample size minus 1. Now, if you go to a more complicated, a next stats class, you may see that degrees of freedom is calculated in different ways, in different situations. But for us in this class, degrees of freedom is always calculated as sample size minus 1. So basically, before you can go to this chart, you have to know what your degrees of freedom are. So for us, that's always sample size minus 1. So let's say we're working with a sample size of 10. Well, then degrees of freedom would be 9. So we're only really looking at the row with a 9 right here. Okay? Now, what can we figure out from this table? Well, look at the headings up here. One of these headings says confidence interval percents. So basically, this will tell us what value of t to use for different confidence intervals. So if we had a sample size of 10, and therefore the degrees of freedom were 9, and we wanted to make a 99% confidence interval, well then the t value we would use to do that would be 3.2498. If instead we wanted to make a 90% confidence interval, then we would use 1.8331. Okay? So when you're making a confidence interval for when you do not know the samples, when you don't know the population standard deviation, and all you know is the sample standard deviation, you have to use the t-table to figure out what t-value to use. Just first figure out your degrees of freedom, and then pick the correct column to figure out your t-value. So unlike the z distribution, when we know the population standard deviation, we can use the z distribution. Or if we're working with proportions, we can also use the z distribution. In those two cases, you can just memorize the z-scores that are common. You always use, with the z distribution, if you have a 99% confidence interval, you always use 2.58. Or if you have a 90% confidence interval, you use 1.65. You can't do that with the t distribution because for every different sample size, your values change. So if you had a sample size of 15, then you'd use degrees of freedom 14. And if you want to make a 99% confidence interval, the value changes. Or a 90% confidence interval, again, the t-value changes. So you can't memorize those t-values for confidence intervals much like you could for the z distribution. Now, let us work a few exercises, not really relating to confidence intervals or hypothesis tests, just a few probability type questions. So, a few exercises here. Find the value of t such that the area in the right tail of the t distribution is 0.1 if the sample size is 25. Okay, if the sample size is 25. Now, let's just draw a picture real fast. Okay, so basically a t distribution looks like a z distribution. Again, it's technically a family, but we can say just for sketching purposes, it's basically like a z distribution. So here's my t distribution. We want to figure out the value of t such that the area in the right tail is 0.1, so 10%. So there's some t value over here such that if I shade that much, or about 10%, is what we're after. So t equals question mark, where the area in the right tail is 0.1. Now, we have to pay attention to sample size when we go to our chart, because again, if the sample size is 25, that means degrees of freedom is 24. And so 24 is the only row we're going to look at on this chart. Now, how would you solve this? You go to your chart, and we go to degrees of freedom 24, the row 24, and notice, actually I need to look at this note on the bottom of the chart. I have a note here when I made this chart that says, note, that is a Greek letter alpha. Alpha level for a one-tailed test is synonymous with the area in the right tail under the t distribution curve. So, if you want to know the area in the right tail, then we look at this bottom set of headings here. So, there's three sets of headings here. Don't let that confuse you too much. If you want the area in the right tail, well, then you use this alpha level for a one-tailed test. In Chapter 9, we'll talk about what it means, the alpha level means, but just for the time being, know that the alpha level for a one-tailed test is talking about area in the right tail. So, we want to find the value of t such that the area in the right tail is 0.1 and the sample size is 25. So again, we go back to the 24th row. And notice what we have here is 0.1. That's the area in the right tail, like the note at the bottom of the page told us. And so the t value we're looking for is 1.3178. 1.3178. Okay? Take notice of how this chart is different than the z-table. In the z-table, we looked up z-values using the side of the chart and the top of the chart and found probabilities in the middle. So like if you want to look up z equals negative 2.7, that z value gives you a left tail probability of 0.0034. So the probabilities are in the middle of the chart, z values are on the sides. With the t chart, that is not at all the case. These are all your t values in the middle, degrees of freedom are over here, and you have essentially probabilities up at the headings. So there's really only, using the chart, the only probabilities you can find are, let's see, that's 0.0005, 0.005, half of a percent. I guess that's half of a percent. And then you have 1%, 2.5%, 5%, and 10%. So these are the only probabilities we can find using this chart. If you want other probabilities, you have to use technology. Okay. By the way, I can show you how to use if you have a calculator. If you want to find, let's check our answer. We said the value of t such that the area in the right tail is 10%. We said that was t equals 1.3178. Well, if you go to distributions on your calculator and go to, let's see, t CDF, kind of like we had normal CDF, but use the t CDF, well, we say that t value right here is 1.3178. So our lower bound for this region is 1.3178. Our upper bound, where we're going forever to the right, is just put a bunch of 9s. And our degrees of freedom were 24, so that this should give us 10% if we have the right answer. Or probably really close to 10%. So let's see. Yeah, that's a hair over 10%, but yes, that's just due to a little rounding error. Okay, because this is rounded to 4 places. Okay, let's try another one. So the next one says, find the value of t such that the area in the left tail of the t distribution is 0.025, so that's 2.5% if the sample size is 39. Okay, so again, just a quick picture here. So this time then we want left tail probability. So left tail, and it's 2.5%, so not very much shaded area, but there's some shaded area, about 2.5% there, 0.025, and we want to figure out what is that t value. Now, here's what you have to remember. The t table, always talks about area in the right tail. But we need to figure out the value of t in the left tail. Now, what we have to do in this case is remember that the t distribution is symmetric. So, if we need a value of t that's on the left side of the distribution, we can first find the analogous value of t on the right side of the distribution, and then make it negative to find the answer that we need. So we can't solve a left tail situation directly, so we need to solve the analogous right tail t value. So we need to find the t value such that the area in the right tail is 0.025, and then that'll be some t value, positive. Make it negative will be the one we need. So what's our degrees of freedom? Let's first calculate that. If sample size is 39, then degrees of freedom are 38. So we go to the 38th row. This is on the back page of our chart. Oh, nope, sorry, that's on the very bottom of our chart. Oh, I picked a bad example. I wonder if it'll fit. Okay, so the 38th degree of freedom, row degree of freedom at the very bottom. Let's see if I can fit everything. Okay, not quite. I'm going to zoom out slightly. Actually, well, I won't zoom out because you won't be able to see it. But, okay, so we're going to focus on the very bottom row. So now let's figure out which heading to pick. The heading we're supposed to pick is, now I forgot, I think it's 2.5. Yeah, 2.5%. So I go ahead and find the 2.5%. Again, we're looking at the bottom set of headings here because that's alpha level for a one-tail test is like the area in the right tail. There's 0.025. So we're going to be looking at this column. That's the third to last column. So go all the way to the bottom. Go down to the 38th row. The third to last column. And we get t equals 2.0244. But that is the value of t such that the area in the right tail is 0.025. We want to the area in the left tail, so what we do is we just take the opposite of that value. 2.0244, make it negative. So negative 2.0244. So what we had to do was, first, figure out the value of t such that the area in the right tail was 0.025. We found that from the chart to be t equals positive 2.0244, but we wanted the value of t in the left tail such that the left tail area was 0.025, and so we found that by taking the opposite of the 2.0244 to get our final answer is t equals negative 2.024. Test. Okay. The mic went off just briefly. Sorry about that. Okay. Now, let's see. What else? Find the value of t such that the area in the right tail of the distribution is 5% and the sample size is 95. Okay, so sample size is 95. Let's draw another quick picture. So the area in the right tail is 5%. 5 something 0.05 right there, and there is some t value there. Now, right tail is what we like, because that's what we can solve directly. And we go to our chart. Now, first of all, degrees of freedom is sample size minus 1, 94. Okay, so we go over here, and notice there is no 94. What you do for any degrees of freedom bigger than 75 is you just use the bottom row. Okay, so we're using the bottom row. And we are looking such that for the value of t, such that the area in the right tail is 5%, 0.05. So we simply go to the 0.05, the second to last column. Now our degrees of freedom, we're going to use the infinity row down here because we use that row for any degrees of freedom bigger than 75. And we see that we get 1.6450. 1.6450 is the value of t we're looking for. Again, we can verify our answer by going here. I'll use the TI-83 this time. By going to the distribution menu, looking for TCDF. And now, okay, for here, we have to know the syntax. It's lower, comma, upper, comma, degrees of freedom. So we're starting at 1.645, shading forever to the right, and then our degrees of freedom was 94. And notice that it's approximately 0.5. Now the reason that it's not really, really close to 0.5 is because the calculator can actually calculate degrees of freedom for any sample size you give it. This bottom row basically is acting like the sample size is not infinity, well, basically like a very, 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 very big sample size. Okay? Here, the calculator is actually using degrees of freedom 94. So whereas the answer is very close here, we should have gotten 5% exactly. We got a little bit over 5%. Really no way around that, and that's just a discrepancy between the chart and the calculator. Okay, let's do a few more here. Find the value of t such that the area in the left tail of the t distribution is 0.0005 and the sample size is 116. So notice, again, if the sample size is 116, our degrees of freedom is 115, and our degrees of freedom doesn't go up to that on our chart, so we're going to be using that infinity row. Now, left tail probability, just a tiny bit of area is what we're shading here. A tiny bit, 0.0005. Now, we're going to be working off of the bottom row of our chart, and we're going to look at the 0.0005. That's the first column in our alpha level 4 one-tail test, the headings we're looking at. So the t value down here is 3.2915. But remember, that's the value in the right of t in the right tail, such that the area in the right is 0.0005. We want the area in the value of t such that the area in the left tail is 0.0005. So we take the opposite of this value and get negative 3.2915. So t equals negative 3.2915. If you wanted the area in the right tail is 0.005, 3 zeros and a 5, then it would be positive 3.2915. Now, these last two problems are related to confidence intervals, because notice what they say. Find the two values of t such that the area under the t distribution between the two values is 0.95, 95%, if the sample size is 11. Okay, so let's draw a quick picture. So we want to shade 95% of the area between two t values and then figure out what those two t values are. And now these are actually really easy with the way I devised this table, because there's a t value down here. Sorry, it's a little cramped here. There's two t values right there and right there. And we know that 95% of the area under the curve, I don't think I mentioned this earlier, but the area under the curve has to be 1 because we're talking about a cumulative probability distribution. So just like the area under the z distribution was 1, the standard normal curve, the area under the t distribution is also 1. Now, the way I have the chart set up, you'll notice, but before we go there, sample size is 11, so degrees of freedom is 10, sample size minus 1. So we're going to be looking at the 10th row, but now instead of looking at these bottom set of headings about the alpha, the area in the right tail, we can look at confidence interval percents. Because when I ask the question, find the two values of t such that 95 or 0.95%, 0.95 is the area under the curve between them, that's asking about a confidence interval. So 0.95 is 95%. So there is a 95% heading, and the t values we're looking for, the one on the right side is 2.2281, and the one on the left side is negative 2.2281. So 2.2281 is this t value over here, and this t value over here on the negative side is negative 2.2281. So that's our two t values, negative 2.2281 and positive 2.2281. Okay? Again, so the confidence intervals are super easy to figure out on the t table, much quicker than the z table, at least to start with. Next question. Find the two values of t such that 99.9% of the area under the t distribution is between those two values of t. So now, I mean, we're basically shading everything. I'll leave a little bit non-shaded. So we're basically shading the entire curve. 99.9% is shaded, and there's a t value over here that's going to be negative, and a t value over here that's going to be positive. So it's 99.9%, it's 0.999, or you can write in percent form if you want. All we have to do, notice the sample size is 45, so degrees of freedom is 44. So we go to the 44th row. (44). And notice we have a heading for confidence interval percents, 99.9. So the two t values we're looking for, the positive one is 3.5258, 3.5258. And the other one is negative, 3.5258. Now remember, just like with a confidence interval using a z-distribution, when we make a confidence interval, we only need the positive one. Okay, technically you could use either one, you get the same answer. But if we were going to make a confidence interval, 99.9% with a sample size of 45, all you need is the 3.5258. But I wanted to show you, how to find the positive t value and the negative t value, because being able to navigate this chart is important. We'll use this chart, continue to use it in Chapter 9 when we talk about hypothesis testing. And if you take more statistics classes, you'll have to use the t-chart in the future or use technology. By the way, there is an inverse t value button on newer TI calculators. So real fast, I'll show you how to find some of these using that button. But again, not all the calculators have it. I've noticed that some calculators that look like they're the exact same model have the button, some don't. I guess the newer ones do. And even though I've seen some calculators that look like this that don't have the button. So if you do have the button, you can double check. Where you go is go to your distribution menu, and if you want to see if you have the inverse t button, just like you would have the inverse norm button. So it's right below the inverse norm button. And basically it does the exact same thing the inverse norm button does. It figures out the value of t such that the area, but get this, in the left tail is some value. So the calculator always operates talking about left tail with the t distribution, whereas the chart is always operating talking about right tail. So real fast, if we want to find the value of t such that the area in the left tail is 0.0005 and the sample size is 116, well, all we have to do is type in area in the left tail, 0.0005, degrees of freedom, 115, and let's see what we get. Negative 3.377. Now, the reason for that discrepancy is, again, because we were operating off the bottom row of the chart, and this calculator is operating as if it had a chart with row 115. Here, so let me show one that's not going to lead to a discrepancy. Just really fast here, so we're almost out of time. And let's see, where did we not have to use the bottom row of the chart? Here's one we didn't have to use the bottom row of the chart. Here was sample size was 38. Okay, so this we should get the exact same answer that we got using the chart. The discrepancies between the chart and calculators, basically it's the chart's fault, because the chart has to make rounding judgments and what rows to include, how many decimal places. The calculator is doing the right thing, and well, using the chart's not ideal, but that's what we do. So it's not a big deal. It's just kind of unavoidable. But we should get the exact same, or get a very close answer here. So, because we don't have to worry about using the bottom row of the chart this time. So here, the left tail probability, let's see, distributions inverse t, the left tail probability was 0.025, degrees of freedom were 38, and let's see if we get that precisely. Negative 2.0244, yes, precisely when rounded. Okay, I guess that sounds weird, precisely when rounded, but yes, if you round this answer, you get that. Okay, so, when you don't have to use that, things get a little weird when you use that bottom row of the chart, but that's kind of unavoidable. Otherwise, using the calculator will get you precisely the same answer. By the way, if you want to find, this first question was find the value of t in such that the right tail area was 0.1. Well, again, your calculator is going to give you the left tail answer. So if we do inverse norm, the area in the tail is 0.1. Oh, that's the wrong button. Inverse t, area in the right tail is 0.1. Degrees of freedom were 24. This is going to give us negative 1.3178. Oh, sorry, you can't see that. That gives us negative 1.3178 because the calculator is working with area in the left tail, but we want the area in the right tail. So we have to take this answer, make it positive because the calculator is operating off area in the left tail. Okay, so just make sure if you want to use the calculator is a great tool, but you just make sure to know what it's telling you. Calculator inverse t, left tail. Chart is always dealing with area in the right tail. All right, let me know if you have any questions. Talk to you soon. Have a good day.